Hi everyone. So today we're going to talk about the cross product. Now the goal for this presentation for me is not for you guys to like memorize that crazy equation for the cross product that I'm going to show you from the book. But I kind of want you to see how it's derived and see how this is different from the dot product. It is a little bit more complicated and I apologize if I'm going very fast. Again, this is kind of just an explanation video. It's not really something that you're going to really need. You might need it for a couple problems, but I don't know if something like this would really come up on the AP test. So let's talk about cross product. Now the definition, very dense definition of cross product is when we're given two linearly independent vectors A and B, the cross product A cross B is a vector that is perpendicular to both A and B and thus normal to the plane containing them. Remember, normal means perpendicular. It's like the normal force is perpendicular to whatever surface that we're resting on. So given A cross B, we get A times B times the sine of theta. And we've seen this before with torque, right? Torque is R cross F, and that's R times F, force times the sine of theta, where theta is the angle between A and B in the plane containing them. Hence, it is between 0 and 180 degrees. A and B are the magnitudes of vectors A and B, and N is a unit vector perpendicular to the plane containing A and B in the direction given by the right-hand rule. Now, an important thing to note here, those double bars, it just means absolute value here. So we want the absolute value of the A vector and the B vector, thus the magnitudes of those vectors. So this right-hand rule, you probably saw this in my torque presentation, but remember your fingers will point in the direction of the first vector in your cross equation. So A cross B, your fingers point in the direction of A, fingers curl in the direction of B or sweep in the direction of B, you might hear, and then your thumb points in the direction of A cross B or your resultant vector. Some people do it like this, where the pointer finger is your first A vector, your middle finger is your B vector, and then your thumb is your resultant vector. Notice how these are all perpendicular to one another. And that's the really important part of this cross product, is that our vectors all have to be perpendicular to one another. How to apply cross product. So we have both the cross notation A cross B and the name cross product. You might also see vector product. That's how they describe it in chapter 3 of your book. We're possibly inspired by the fact that each scalar component A cross B is computed by multiplying non-corresponding components of A and B. We only multiply non-corresponding components of A and B, as in like the I hat and the j hat, or the j hat and the k hat, or the k hat and the I hat, not A and B, blah, 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 because the corresponding components multiplied together are equal to 0. Meaning when we have I hat cross A hat, I hat, j hat cross j hat, and k hat cross k hat, those are equal to 0. Okay, so corresponding components, what they mean by that, those are parallel. And we know that the sine of 0 or the sine of 180 degrees, so when two vectors are parallel to one another, either in the same direction or opposite directions, then we get 0, because the sine of 0 is 0 and the sine of 180 is 0. So this is the whole reason that cross product is more complicated than dot product, because remember with dot product, so like work, remember, is a dot product. And what happens with that is these are all equal to 1, and then everything else is equal to 0. So it's much less complicated than cross product. But this is kind of the definition here, why we use sine also. This is our like definition of cross product, because we want all those different vectors, right? Our A, B, and then the resultant are all going to be perpendicular to one another, and these are not perpendicular to one another. So what happens here is if we use the right-hand rule, we can find the resultant vector. So the standard basis vectors, I, j, and k, satisfy the following equalities in a right-hand coordinate system. So if we use our right-hand rule, we can see the direction of the resultant vector. So if you point your fingers in the direction of the positive x-axis, that will be our positive I hat. This might not be the right direction because sometimes this is mirrored, but I'm pointing my fingers to me in the direction of the positive x-axis. I'm curling my fingers in the direction of the positive y-axis, and then I get a resultant vector in the direction of the positive z-axis, or my k-hat direction. You can do the same thing with all of these to, kind of prove it with your right-hand rule, but these are what we get when we use these different directions in place of, those directions of A and B when we're crossing those vectors with one another. And then with the anti-commutativity, so hard for me to say, when we flip these, we get a negative vector. And again, you can do this with your right-hand rule. I would point my fingers in the direction of the positive y-axis, curl my fingers in the direction of the positive x-axis, and I get a negative z-axis for that, which is why I get a negative k here. So I encourage you to see how these work with your right-hand rule, okay? Remember, you point your fingers in the direction of the first one, curl your fingers in the direction of the second one, and your thumb points in the direction of the resultant vector. So what happens here, the reason we go through all of that and the right-hand rule and all that stuff, is that when we have two vectors, and say they're both in 3 dimensions, so they have an x component, a y component, and a z component, and we get them in unit vector notation like this. So our two vectors, and for some reason, when I found this stuff online and copy pasted it into this PowerPoint presentation, they use u and v, which look very similar when they are cursive, like you can see here, which is very frustrating. I'm sorry. I would type it all out with A and B to make it look nicer, but that's just going to take me forever. So I apologize. So we have two vectors, u and b, can be defined as the sum of 3 orthogonal components parallel to the standard basis vectors. Basically, you have the u vector in 3 dimensions and the v vector in 3 dimensions. Their cross product, u cross v, can be expanded using we're distributing. I can't say that word. We're distributing here, okay? So what happens here is we have our u vector crossing our v vector, and you take each term and then you're going to distribute it to every single term in the other vector, okay? So we get u1i times v1i, so that's what this is right here, u1 times v1, and then I cross I hat cross I hat, and then u1i times v2j, u1 times v2, I cross j, so on and so forth. I'm not going to go through every single one here, but that's the first step here, okay? Notice that u1 is your x component of the u vector, u2 is your y component of the u vector, and u3 is your z component. So 1 is x, 2 is y, 3 is z. Now, once you have all this, then you have to remember that I hat cross I hat, j hat cross j hat, and k hat cross k hat are all 0. So all of these cancel out because they're all equal to 0. With all these other ones, you then have to use the right-hand rule in order to find the resultant vector. Okay, so I hat is your positive x, j hat is your positive y, fingers go in the direction of positive x, fingers curl in the direction of positive y, and you get a resultant vector in the direction of positive k. So, or z, right? So this becomes k hat here, okay? So from this decomposition, by using the before mentioned equalities and collecting similar terms, we obtain this. So again, this is, remember I said that becomes 0, right? Because I hat cross I hat is 0, our j hat cross j hat is 0, and then our k hat cross k hat is 0. So that's where those zeros came from. And then k, I showed you how I got that with I hat cross j hat from this before. Okay. Now, these minus signs, these are coming from when we get a negative axis. So for example, we have a minus u1 v1 v3j. That just comes from this right here. Oops, sorry. This right here when we cross I hat cross k hat. So you'd point your fingers in the direction of the positive x-axis, curl your fingers in the direction of the positive z-axis, because that's positive k, and then my thumb point down here. Okay, so since my thumb is pointing down, that's a negative y-axis or a negative j, which is why you have this negative in front here. Okay, again, I'm not going to go through every single one there, but that's where those negatives come from here. Now we're just going to combine like terms, meaning we're combining the I hat with the I hat, we're combining the J hat with the J hat, and we're combining the K hat with the K hat. So you end up getting this whole thing right here. And that's your final equation, okay? That's the final equation that you can use for these cross product problems. Now, this is also in page 53 of your book. It's written a little bit nicer because it's actually written with A's and B's instead of U's and V's. Like, who made that up? But here you can see, sorry, my little thing came up. But here you can see we have A cross B, and that's equal to AY BZ, and they're multiplied together, right? AY times BZ minus BY times AZ I hat. And you can see the same thing above with the U's and V's. Remember, U is like your A vector, V is like your B vector, 2 was Y, 3 was Z, and 1 was X. So you can see that that's the exact same equation that we got with the U's and V's before. All right, so this is page 53 in your book. You might want to write that equation down just because it might come in handy later for maybe a practice problem or two. But we're not going to do too many crazy problems with cross product like this. Now, a little easier, it's not really that much easier, but it's kind of an easy way if you can't remember how to do these problems. There's something called Soros Rule. So the first thing you have to do is you have to use matrix notation. And so when you have U cross V here, the way that you would write this in matrix notation for Soros Rule, you write I hat, J hat, K hat across the top, and then you have your X component of U, your Y component of U, and your Z component of U, your X component of V, your Y component of V, and your Z component of V. Now the next thing you're going to do here is some fancy schmancy artwork, I don't know. And all you do basically is you circle, starting with that I right there, you circle diagonally. And you also, I forgot to mention this, you have to also write the I, J, and K down below and the U1, U2, U3 down below that. So you can see I, J, K is written, U1, U2, U3 is written. You then circle diagonally from right to left down for your positives. And then again, you circle diagonally starting with the K from right to left up for the negatives. So you can see you have I times U2 times V3 here plus U1 times V2 times K plus V1 times J times U3 minus V1 times U2 times K, and so on and so forth, so you get this, and then again you combine your K's together, you combine your I's together, you combine your J's together, and what this ends up giving you is it ends up giving you those big equations right here, this one right here, and your A, the same thing as A cross B, right, where U is A and V is B. So that's kind of a quick way to get your cross product like big equation. This is called Soros Rule. So it's just a kind of technique to remember this equation, I guess. Now, again, I wouldn't memorize this entire equation. I wouldn't even really memorize this Soros Rule. I just wanted you guys to kind of recognize why cross product is the way it is and where that equation on page 53, where that comes from.